Hey everyone, and welcome. So, if you're diving into the world of pharmacy or medicine, you've probably already bumped into this huge fundamental challenge. How do you get a drug to actually work once it's inside the body? Well, that's the whole field of biopharmaceutics in a nutshell. And today, we're going to unpack one of its biggest puzzles, what we call the bioavailability challenge.
I mean, think about it for a second. It seems so simple, right? You just swallow a pill and, it does its thing. But the reality, it's so much more complicated. A huge chunk of that active ingredient might never even make it to where it needs to go. So what on earth is happening on that journey from your mouth to your bloodstream? That question, well, it's at the absolute heart of how we design medicines.
And the answer really comes down to this one key term, bioavailability. It's basically the report card for a drug. It's the measure of how much of that drug actually gets into your circulation, ready to do its job. You see, low bioavailability is pretty much the arch nemesis of an effective medicine, and it's the exact hurdle that pharmaceutical scientists are working like crazy to overcome every single day. So how do scientists even start to tackle a problem this big? Well, they don't just take a wild guess. They use a map, a kind of scientific framework for diagnosing the problem. It's called the Biopharmaceutics Classification System, or BCS for short. And trust me, this is an absolutely essential tool you're going to want in your toolkit. This whole BCS map is built on two really fundamental ideas. First up, you've got solubility. Pretty simple. Can the drug even dissolve in the fluids in your gut? Because, if it just stays a solid little rock, it's not going anywhere. Then there's permeability. Okay, so it dissolved. Now can the drug molecule actually get through the wall of your intestine and into your blood? A drug really has to be good at both to be easily absorbed. And this table just lays it all out perfectly. You've got four possible outcomes. Class 1 drugs, they're the star students. High solubility, high permeability. They get absorbed like a dream. But then look at Class 2. They're good at getting through the barrier, high permeability, but they just don't want to dissolve. So the whole challenge is just getting them into solution. Class 3 is the total opposite. And Class 4 drugs, well, they're the toughest puzzle of all, low on both solubility and permeability. Each class is a totally unique challenge. And when a new drug comes along, scientists use a super simple decision tree just like this one. They just ask two questions. Is it permeable? Yes or no. Is it soluble? Yes or no. And by answering those, they can immediately slot the drug into one of those four classes. This tells them exactly what kind of bioavailability problem they're up against and points them straight toward the right set of solutions. Okay, so let's jump into the first set of solutions. These often target those really tricky Class 2 drugs, the ones with low solubility. And the guiding principle here is actually surprisingly simple. If you want something to dissolve faster, you just make it smaller. The most common way to do this is with a process called micronization, or you might hear it called micromilling. The logic here is just pure physics. Think about it. By grinding the drug powder into teeny tiny particles, you massively increase the total surface area that's exposed to the fluid in your gut. And more surface area means a way faster dissolution rate. It's that simple. So how do they actually do this? Well, this diagram shows a jet mill. Basically, you feed the drug particles in and then just blast them with high-pressure air. This makes them smash into each other at incredible speeds, and that collision is what breaks them down into much finer micronized particles. It's a really elegant and powerful mechanical solution. But what if you need to go even smaller, like down to the nanoscale? For that, we need something a bit more advanced. Supercritical fluid recrystallization. Now, I know that sounds super complex, but the idea is actually fascinating. It involves using a substance, usually carbon dioxide, in a very special state of matter. Just take a look at this phase diagram. If you take a gas like CO2 and you crank up the pressure and the temperature past a certain critical point, it enters this whole new phase. It's not really a liquid, and it's not really a gas anymore. It's a supercritical fluid. And the amazing thing is, it has the power to diffuse like a gas, but dissolve things like a liquid. This makes it the perfect super-tunable solvent. So here's the magic trick. Scientists take the drug, the active pharmaceutical ingredient, or API, and they completely dissolve it in this supercritical CO2. Then they suddenly release the pressure. The CO2 instantly turns back into a gas, and poof, it can't hold the drug anymore. The drug immediately recrystallizes into incredibly tiny, uniform nanoparticles, which are now perfectly set up for super-fast dissolution.
Okay, so we've seen how you can physically shrink drug particles down, but what if we use a little chemistry to help the process along? This brings us to another key tool for formulation scientists, chemical additives, or as I like to call them, helpers, like surfactants.
Surfactants are basically wetting agents. They work by lowering the tension between the solid drug particle and the liquid around it. What this does is it allows water to get into the nooks and crannies of the powder way more effectively, which, you guessed it, speeds up dissolution. This is a technique that has been a real game changer for improving the performance of drugs like the steroid spironolactone, giving them that much-needed bioavailability boost.
All right, we've looked at some pretty cool specific techniques for improving how drugs dissolve. Now, let's kind of zoom out and see how all these tools fit into the bigger picture. When it comes to designing more effective medicines, there are really three core strategic approaches. First, you've got the pharmaceutical approach. This is everything we've been talking about, changing the recipe or the formulation with things like micronization or adding surfactants. Second is the pharmacokinetic approach. This is where you go a step further and actually modify the drug molecule itself, maybe by designing something called a prodrug. And third, there's the biological approach. This is where you change the delivery route entirely, like forget the pill and move to an injection instead. You see, understanding these challenges and all the tools we have to solve them is absolutely fundamental to modern medicine.